Hello everyone, and welcome to today's session. My name is Matt Westerway. I am a driving simulator engineer at VI Grade, and I'll be your host for today. As usual, this webinar is being recorded, and the video will be made available on our webpage soon. And also, before we get started, please make sure you have your microphone set to mute and remain muted throughout the presentation to avoid any accidental interruptions. Joining me for today's session, first of all, is Francesco Ambrogi, Global Service Manager at VI Grade, and shortly he will be giving a live demo of VI Motorsport. Then also joining me today is Vince Van, Application Engineer at VI Grade China, and also we have Giuseppe Tranquillo, Vehicle Dynamics Engineer at Megaride, and later in the presentation they will be giving, they will present the use case of the modeling and evaluation of a DAS system within VI Motorsport, specifically including tire thermal effects. Finally, at the end of the presentation, we'll have a Q&A session. And throughout this presentation, you can use the chat functions. So if you have any questions, please use the WebEx chat function to send your questions directly to the VI Grade WebEx chairman, and we will collect them and answer them at the end. So let's start by talking a little bit about motorsports with VI Grade. It's well known that the motorsport industry is an incredibly demanding environment where absolute performance is the ultimate goal. Currently, VI Grade software and simulators are being used by some of the greatest names in motorsport and has already proved to be a valuable tool in helping them to achieve big results and important results in the WEC and the Formula E championships. We believe this added value is coming from the fact that VI Grade is providing a complete software package, including all of the features needed to perform simulations and design studies. And as well, an important factor is that we're also providing a direct link from the software to the driving simulator. And of course, the driving simulator is allowing for not just setup preparation, but key driver training and this loop between the driver and the setup. So when you head to the track, you've got a head start. So now I'll hand over to Francesco, who will show you how VI Motorsport works in practice.
Thank you, Mark. Hope everybody can hear me well. So what we are going to talk now is what is VI Motorsport about, and which is the workflow that is typically used to set up the simulation that can be used to prepare and to support on-track sessions. We typically go, as in many simulation environments, through a process in which we start building the models. In this specific case, we want to deal with a vehicle model, a fully dynamic vehicle model, which has also an interaction with the environment. So we also need the track to be an important part of this process, and we need to collect all the information that are needed to come up with a consistent simulation. VI Motorsport is supporting this requirement using a set of tools and accessories that are helping the user to implement the vehicle model subsystem, as well as the environment and the preparation, for example, of driver lines, which are a fundamental topic to be covered. Once the model is available, it is possible to perform simulation, and this is of course possible in an offline environment, which is the first item that is considered. But it is also at the same time possible to use the same simulation model in a driving simulator environment in a way that also the driver can interact with the model and retrieve the needed information, let's say, before the on-track session. In this process, which is typically iterative, it is also possible to apply modification to the vehicle model and to study the effect of the changes in the different subsystems and components on the performance. So using the analysis features like the max performance that we are going to showcase in a few moments, or the investigation mode that is allowing to provide a design of experiment on specific events, it is possible to come up to an optimized setup for the vehicle. So basically, just summarizing the different steps that are taken to come up with the final setup, we start from the creation of the model, which is consisting in implementing the different subsystems data, and this can be done collecting information from a variety of sources, putting together track data, and this can be done either using laser scan information when they are available, or in cases where it is not possible, just relying on GPS data, or even basic data retrieved from Google Maps, Google Earth. And then, of course, we perform simulation to define the performance KPIs and define a proper setup. In this loop, as I said, we are talking also about supporting a driving simulator session and refining and improving the simulation model using specific additional analysis. So now I can demonstrate the typical showcase. You should be able to see my screen. So where do we start from? Basically, we need to have some information about the subsystems that we want to create. Typical point is about suspension data. VI Motorsport is supporting the creation of model suspension information using a tool which is named VI Suspension Gen, which is allowing to create directly a simulation model for the suspension. The environment is taking care of converting the pickup points that are available in the system with so we are starting from the geometry of the suspension that can be converted into lookup tables used for the simulation. This is typically done either retrieving data from the CAD or using CMM machine to measure the points from a physical prototype. So, for example, if you set up a simple Excel sheet with all the geometric information, this can be easily converted into an input file for VI Suspension Gen, which is the application where this data can be analyzed. So if we go in VI car real time, which is the main element in VI Motorsport, we can just fire up VI Suspension Gen, and we can load the data from the property file that is created by the geometric pickup points. The tool is providing the possibility, of course, to modify the different points and properties for the suspension, and it is also capable of showing the effect of the geometry changes and other changes on the typical suspension characteristics. So, for example, here we have a specific setup for a suspension. We can analyze it, and we can also modify the geometry for example, changing their point position. Say we change this value and we run a new simulation, new kinematic analysis. So as you can see, I am able to compare directly the effect of the geometry change on the suspension curves, and so I have already an idea of what is about the modification that I'm making. As soon as I'm satisfied with the setup that I've obtained, I can just publish the resulting subsystem in the VI car real-time database. And I'm able to basically work in the environment which is now focusing on the full vehicle. So we have in VI car real-time the possibility of defining the model using different subsystems, and the information is stored in specific files within a database. The model that I've just created is accessible from the database, and I can use it for running tests that are specific of the vehicle model. Of course, I will also have to populate the additional data for the model with regard to the other system information. So, for example, global information for the body, aerodynamic maps, powertrain information about how the vehicle is going to be configured, wheels, brakes, and all the subsystems. When the model is complete, I can set up a fingerprint for testing the different configuration that I want to study with a specific full vehicle events. So, for example, here I could change the position of a pickup point in the front suspension and see the effect on the braking performance of the system. So I can set up a braking event, and in this event I can analyze the two geometric configurations. Now I do not spend the time to run the simulation. I already did before. I move in the last, the third use mode, which is the review mode, and I can just analyze the resulting configuration. And so, for example, in this case, I can see for this vehicle model the effect in the braking event on the pitch that the vehicle is subject to under hard braking. Okay, next point is about how we do integrate this vehicle model in a track simulation and full track analysis. So the need of data is related at this point to track information. As I said, one possibility is, of course, to use laser scan data, which is providing a very detailed description of the road. But sometimes this is not possible, and if you want to perform your simulation, you need to rely on less accurate data. So, for example, if you can get track shape and track information from Google Earth, it is possible to use this information to set up a first road simulation model. So basically, here we have the Las Vegas roval track, which has been, let's say, created using Google Earth. And this information is typically producing a KMZ or KML file that can be imported in the other tool, which is fundamental for the VI Motorsport package, which is VI Road. Basically, VI Road is an application that we can launch from vehicle real time, where we can simply manage road data. So what is possible is to just import the KML data or KMZ data for the center line and create a road model out of that. So in this case, we are just using the center line, and then we specify a width for the track. Okay, so maybe I have just one version that I already converted. This model can be, of course, also enhanced with some additional information. So, for example, if you want to include curves, this is something that is possible directly within the tool. For example, I can include the curves for the first chicane, and I can just modify the values for the arc length I want to apply curves to. As you can see here, I've included the curves in the surface representation of the road. But the other important thing that is possible with VI Road is that I can study the different driver lines directly within the tool. We have a functionality which is called corner cutting, which is allowing to basically create a specific driver line according to the level of cutting that I want to use in a specific turn or for all the track. So very simply, just with the design parameter, I can create different options for the driver line that I want to use, and this is done typically by an automatic algorithm. But at the same time, I also have the possibility of defining specific points where I want to have the driver line passing through. So, for example, in this straight, I want to include some control points. And I can just implement a new driver line. So now the shape is not perfect, but it gives the idea that you can prescribe the driver line to go through specific points. So once this information is available, these data are available, and you have the road surface and you have the driver line surface, it is time to run a full vehicle simulation. This can be done using the max performance event, which is available in VI Motorsport, and basically it is consisting in a two-step algorithm, which is first of all computing a velocity profile on a given driver line, the one that we have just studied and selected. And at the same time, and in the next step, the algorithm is solving the dynamic equation of the vehicle model in a way that the velocity profile is used by a dynamic virtual driver to achieve the maximum performance. And the interesting fact is that this is going to be using the full vehicle dynamic model, and this is so very accurate. So when we set up this event, we basically do prescribe the driver line. Of course, we provide information about the road surface that you want to use, and we define some parameters, which are the distance that is allowed for the driver to pass far from the driver line, and then we also can use some performance factor to, let's say, push or more or less the aggressivity of the driver. This simulation is basically run again from the same environment and can be, when it is executed, can be loaded and visualized in the VI Animator tool. So in this tool, we can, of course, implement the telemetry data that are typically used. We can create different tabs with the views on the channels that we are interested into, and we can have also an animation of the vehicle simulation while it is running. So we can, let's say, also visually analyze the behavior of the vehicle. In this context, of course, it may happen that for specific tracks where we have not laser scan information, we do not have full detail of the road surface, and so we need maybe some additional insight about how we can tune the vehicle model in terms, for example, of damper settings, in a way that also the road irregularities are being considered in a proper way. And one example that I can show here is about how it is possible to combine information from telemetry data with the so-called 7-post event in VI car real time. So the idea is that we are going to use the telemetry data, specifically the up accelerations that can be recorded on the specific track, maybe so coming, let's say, from previous season, if they are not available for the current track setup. And these time histories can be used to excite the vehicle model and to analyze its response in a dynamic test rig. So what is done in this case is to convert the time histories from the telemetry into an input file for a specific event, which is the 7-post. So in this case, we are basically providing for a simulation a input file where we have the time histories of the 4-corner acceleration and also down forces, longitudinal acceleration for compensation purposes, and steering input. So this event, even if we do not have the very detailed representation of the road surface, can be used to review the behavior of basically the right behavior of the vehicle, considering all the components. So in this case, for example, I have a vehicle model and I have different settings for the dampers. Basically, the simulation is providing actuation on the wheel hub or wheel contact patches, and can be used in conjunction with specific setup that I wanted to apply to the system components. So this can lead to the definition of a setup of the vehicle. And of course, the model as it is resulting from this analysis can then be used for setting up again a full simulation. Another step, so it is then to go on the track, and it is possible to, let's say, see the results that are coming. So we can, for example, import telemetry data for the same track coming from a real session, and we can either validate or use as a reference for specific simulation. So you see here a telemetry data that has been basically recorded on the Las Vegas track. And the interesting fact is that the model is matching the telemetry. Of course, there are some mismatches, but the main behavior of the vehicle is captured. And this was done, so the model setup was done before the track without a specific tuning or validation. So it is interesting that it's possible to come up very nicely to the behavior of the vehicle, let's say upfront to the track session. Also here you can see that the damper displacement are pretty similar. Of course, here we have some offset related to the fact that the measurement in the telemetry are offset with respect to the static condition, while in the simulation model we have the design condition as a reference. But the shape of the curves, as you see, is pretty close. Next step is about how we can, let's say, improve or optimize the behavior performance of the model. And of course, we can apply manually changes, but we can also use the so-called investigation mode. The investigation mode is basically an environment in which we can vary some of the model parameters in a way that the application is then monitoring specific car targets and comparing the results of the different model configuration. So very simply, if we take the simulation, the one existing simulation, so for example the track lap that we have studied with the maximum performance, we can define within the set of model parameters. So for example, we could pick up a bunch of properties like the anti-roll bar stiffness. So just to make a very simple example, we can define the anti-roll bar stiffness as a factor that we want to study. And we just promote it into the simulation environment. For the specific factor, we can define values in a range or providing a specific values, and also we can define responses that we want to study. So in our case, for example, if you want to optimize the lap time, we can define a factor which is the maximum value of the time channel, or we can have average speed or whatever other quantity that we want to use. So at this point, basically, we do set up a combination of parameters that can be studied. For each of them, we run a single or multiple simulation. And at the end of the process, we can review how the different setup performed the one respect to the other. We have the possibility of accessing the design space, also in a web HTML report. And so, for example, here you can see in this table the combination of front and rear anti-roll bar ground stiffness, and we can compare the resulting lap time and average speed, but basically whatever parameter can be monitored. And we also have the possibility of representing these results in a parallel plot. So you can just pick up the, let's say, configuration with a lower lap time, the smallest lap time. So we see that it is number 7. We can just apply one variant to the model, and so we just go back and, let's say, apply the model parameters in the optimal configuration into the vehicle model. Okay, so this is just an overview. Of course, there are a lot of things that can be additionally done, and yes, I invite you, if you have questions, to raise them, or let's say to get in touch with us for a deeper discussion if there is a specific application that you want to address. So I think now it's time for me to hand over to Vince, who is going to talk about the next topic.
Hello, here is Vince speaking. Can you see my screen? Yeah. I'm Vince Wang from VI China, an application engineer. So here we are going to talk about something of adding advanced motorsport mechanical and control system to our simulation. Here, as you can see, is a Formula One car from Mercedes-Benz AMG Petronas. And they have developed a DAS system at the beginning of this year, which has caught a lot of attention from motorsport and automotive engineers. As we may have already know, the race driver pulls out the steering wheel on the long straight line, and then the toe angle of the front wheel will change simultaneously. There have been a lot of guesses about the mechanism behind this. And here on the right side is just one of the speculations. And as a vehicle dynamic engineer, we usually will be more focusing on the benefits of the DAS system. How does it improve our vehicle behavior? Does it helpful to improve the lap time results? So here are some guesses of the benefits according to automotive and motorsport medias. Firstly, as our common sense, if the toe angle decreases, then the tire drag force will be reduced, and the lower slip angle of the front wheel will also be helpful to control the tire temperature. Then, for an open wheel race car, for example, Formula One car, the toe angle of the front wheel will also have some influence on the airflow. So if we use the advanced aerodynamics map in VI Motorsport, we will have this formula listed on the right side of the screen. And you can see that we have additional vehicle effect, and then you can consider the wheel steer angle. If you have the data from wind tunnel or from safety simulation, you can model this effect in VI Motorsport. And for tire drag reduction and tire temperature benefit, we will use an advanced tire model to model this effect later. So here we need to build a vehicle model in VI Motorsport. So we are using Vehicle Wizard and VI Suspension Gen to create a basic vehicle model. And then we tried to modify the vehicle parameters, and according to the Formula One official onboard telemetry video, and we can try to match the overall performance of the race car. So here you can see the acceleration results of the simulation. And here the deceleration results. So we normally change the aero maps and the tire behavior as well as the suspension to match those curves. Finally, we are using laser scan the Hockenheim GP circuit to do lap time correlation. We have modified the vehicle parameters, then we tried to match the lap time and tried to match the coloring limits of the race car. Then with a validated vehicle model, we need to add the DAS control function in VI Motorsport to do what the driver do on the racetrack. So as you know, VI Motorsport has very friendly interface with Simulink. So we have added 2 parts of the code into Simulink. So here in the green color, this code detects the So here in the green color code, this part detects the position of the race car on the track. So if the race car is in the DAS activation zone, which we predefined, then the red part of the code will change the toe angle of the front wheel directly by adding the toe offset. Then finally, we can make the toe angle to get closer to 0. Then when we have the Simulink model, we can also export it from Simulink to VI Motorsport by generating dynamic link library plugin from Simulink. Then we can modify all the parameters in VI Motorsport and get faster calculation efficiency. So let's say something about the results. We have did some simulation about the DAS on and DAS off simulation. And here we can see when the DAS is activated, the toe angle was changed. And then we get higher top speed on the straight line. And of course, we get faster lap time when DAS is activated. As you can see in the video, the red car is with DAS and the blue car is DAS deactivated. Here we also make a simple calculation about the tire drag force to consider the combined influence of the lateral force and the longitudinal force. So if the DAS is activated, then the tire snip angle is reduced. And of course, the lateral force on the straight line will be decreased very, very significantly. But finally, the tire drag force has also decreased, but not too many. So here we have made a comparison between DAS and DRS. So here we can see that DAS can only reduce 100 to 200 drag force and but DRS system can have more than 1,000 Newton drag force reduction. So finally, DAS has not improved the top speed very, very significantly compared to DRS, but it's also very helpful to increase the lap time because you will have more sector to use the DAS system if your driver can handle this. And finally, we needed to use some advanced tire model with thermodynamics to discover more about the benefits of tire temperature and the tire wearing out. So here, let's use from MegaRide to talk about more about the tire model and the thermodynamics.
Good morning. I am Giuseppe Tranquillo from MegaRide, a startup company of Federico II in Naples. Now I'm going to walk you through the details of the used tire model. We know the tires have a fundamental role to reproduce with a high level of details the phenomena concerning the vehicle dynamics in a virtual environment. Tire modeling is not trivial since there is a large amount of interconnected features such as thermal effect, footprint dynamics, and many others. To obtain that, many different tire models can be used with multiple input complexity level and targets. But standard tire models do not take into account the multiple physical phenomena characterizing the real behavior of a tire. We can see that without the data variability related, for example, to thermal effects, the identification of a standard Pacheco tire model can be not reliable due to high complexity level of the tire-road interaction. Thanks to ride suit, which is composed of several physical models, as a multi-contact tire model, a thermal tire model, and a low-speed tire model, the mentioned phenomena can be taken into account to obtain a more physical long-run simulation. We can see in the figure how the tire grip and stiffness vary with the tire temperature. Thermoride model is composed of 8 different layers along radial direction. In lateral direction, the models The nodes are grouped in 3 different ribs to take into account the footprint variation due the steering and camber variation. This model takes into account all physical phenomena related to the thermal behavior of a tire. We can see the heat conduction between the different layers, the heat exchanged with the external environment, heat generation through strain energy loss and friction power, wear effect on the tire, and heat exchanged between rim and brake. To build a more physical tire model, 2 steps are performed. A first physical parameterization to obtain footprint data, thermodynamics coefficients, and many others. And secondly, a model calibration and validation through specific outdoor tests. I'd like to highlight that these steps were carried out at Unina Tire Lab using a non-destructive methodologies. This video shows a simulated sweep of slip angle for a cambered tire. In this video, we can see the results of the thermoride tire model, and we can see how the tire different layers have different temperatures. And looking carefully, we can also see that the heat generation is not uniform over the tire due to the inclination angle. So we can see how the right rib is hotter than the symmetric ones. Adderide model, working in parallel with thermoride model, is completely compliant with the V-grade real time environment. The following outputs are obtained from a co-simulation between Adderide and V-grade max performance through a standard user interface API. To better understand, the following slides show the differences among standard magic formula and Adderide model during our map lap. The latter, in fact, takes into account the effect of temperature and wear on tire performance in real time. To better clarify, these outcomes are obtained using a Pacheco formula and compared that to the new Adderide cold tire and the worn ones. From this figure, we can see the 3 different behaviors and how the classical magic formula is more performant compared to the others because do not consider the thermal effect on tire performance. Now let's focus on the dust effect on the tire thermal behavior. Analyzing the outcomes obtained for Hockenheim GP, we can conclude that due to a lower toe angle in straight, DAS vehicle have a top speed greater than the default vehicle, as shown previously by Vince. But we can also see the differences between the 2 thermal profiles from the front right tire in third figure. Considering a section of the track, we can see how a single maneuver could affect the tire temperatures and how DAS system allows to keep the tire colder due to the decreasing of the friction power and the higher vehicle velocity. So the availability of the DAS system represents a new tuning element to manage the tire temperature and consequently the wear. reminding the correlation between stiffness of the tire and tire temperature, we can assume that an optimal vehicle setup and a correct management of the tire temperature is the key factor to control the vehicle understeer and oversteer attitude. In fact, we can see how a hotter tire have lesser stiffness and vice versa. Now I will leave you with Mark for the conclusion. Thanks.
Thank you, Giuseppe. So, in conclusion, VI Motorsport is a complete simulation software package, including a real-time vehicle model and all of the features required to accurately model your race car, and also all types of optimizations and setup adjustments can be performed and studied to best prepare for a simulator or even a real track session. So if you're interested or would like to know more, then please check out the links currently shown on this slide. And now we will finish with the Q&A session. So you should all see on screen now the question slide. So we'll just run through them one at a time. So first question is, are the tracks laser scanned?
Yeah, I think I already answered that, but maybe I can be a little bit more clear about this. So the road models in VI Motorsport can be differently created, and so it is possible to use laser scan data when they are available. Today we have been talking about let's say the more basic approach in which you do not have this possibility, but the format is supporting both the topologies of data. So laser scan is also supported.
Okay. Then, is there any built-in function that can automatically optimize the racing line?
In VI Road, as you have seen, we have the functionalities to modify racing lines. Automatic optimization is not supported. It can be eventually implemented using some scripting functionalities. So calling the corner cutting algorithm in iterative way, it would be possible also to optimize the race line. Of course, this is not out of the box functionality, but in general it could be possible.
Okay. Then, is it possible to use telemetry data to directly improve the road irregularities model for the max performance simulation?
Yes, in general, it could be possible because in the road model, so the one that we have discussed this morning is a kind of ribbon road where we basically use a nominal surface for identifying the road definition. We can superimpose irregularities that may be either expressed in a space domain, so depending on let's say longitudinal axis of the road, or they can be also implemented in a frequency domain, so it can be provided as a spectrum of irregularities that are retrieved from telemetry.
Okay, then by doing the DAS this way, you basically directly interfering with the tow signals, but without considering the suspension geometry changes.
No, I would say, Vince, you go. Okay.
Okay. Hi, about this question, in VI Car 10, we can describe the back displacement influence on the wheel toe angle and the camber angle, as well as wheelbase track width change. And according to regulation, teams can only change the track displacement on the left side and the right side, but now vehicle time cannot change the rack displacement separately on the left or right side. So we directly add the toe offsetting simulator, but we can simulate the influence about the influence on camber angle and the wheelbase change, track width change, and also add the offset to the Simulink model. So we can consider the suspension geometry changes. Any other information, Francisco?
No, I think this is correct. So in general, we in VI real time we do represent the suspension geometry as a surface lookup function depending on wheel travel and steering input for what regards kinematics of the front axle, and this can be modified by using a difference and offset in the signal as Vince has shown in this part of the presentation. In general, it could be also possible to create a multidimensional map which is completely taking into account the detail of geometry, just not doing the direct linear superposition of the signals.
Okay, so I'm not sure if we picked up this last question on the slide, so I'll just read it out from the chat. The question is, usually how much time, okay, we have the slide, perfect. How long does it take to build a tire model with temperature sensitivity?
Yeah, thank you for the question. I think the answer has to be split in two different areas, because for what concerns the pure temperature parameterization, we usually use 2 or 3 weeks at our tire lab in order to develop the thermal parameters identification thanks to specific certified methodologies, and to get information about footprints and strain energy loss. Then after that, we have to plan a specific test session outdoor with our partner in order to calibrate the model. But the second part of the answer, of course, takes into account about how our customer is able to get the data about tire forces and slip indexes, because of course you can get data from a flat track session, or maybe you have your instrumented vehicle, or maybe you prefer to work with us because we have a methodology called TRIC that allows to use the vehicle as a sort of moving lab. So depending on the kind of way to get the proper data about tire rod interaction, we use those data to parameterize our advanced Pacheco at the ride model. And we couple it with the wear model and the thermal ride model. So the global path, if we are quite fast with partners, employs about 1 month, 1 month and a half.
All right. Then how is the aero map handled in the simulation?
Aero maps in VI real time are basically depending on the ride height of sensors that are placed on the front and rear part of the vehicle. We must say that in general we can have either a basic aerodynamic model where the downforce are expressed as a dynamic function of the ride height, but we do also support an advanced aerodynamic model in which those dependency can be complemented with additional maps. So for example, influence on pitch, yaw angle, and roll angle can be also included into the computation.
Okay. And then how to go from parameters that are usually physically tunable on the car, i.e. suspension clicks and aero flap angles, to parameters tunable on the simulation?
Yes, in general, what is needed is to provide a mapping between those parameter configuration and the physical models that are described in the VI real-time vehicle model. So, for example, for suspension clicks, the different lookup table for the damper should be provided. Or as an alternative, we have the possibility of scaling and offsetting the parameters within, again, within VI real time in a way they are representing the specific configuration. The same can be said for the aerodynamics. So if you need to study a specific flap angle, you will need to provide either a dedicated aero map or take advantage of the modifiers on the aero maps, which are, as I said, this either scaling or offsetting the map output into the simulation.
Okay, I think we have a last question for the Mega Ride guys in the chat. Is it possible to see what tire model you use for low speeds? Flavio, Giuseppe.
Yeah, it's me. Thank you, Mathieu, and thank you for the question. The answer can be a joke because, of course, for motorsport, we don't need low speed. But the real answer is that we developed a specific model concerning the interaction of the tire model in low speed conditions, because I think all we know that the normal magic formula model has some issues at low speeds. So we developed a specific proprietary model. So it's not the literature one. And of course, we cannot give the open equations, but of course, we are totally open to discuss about that with the Sai Kumar that asked us the question and with all the rest of you that are interested in our technologies. Thank you.
We have a last question. Is it possible to build joint optimization between VI real-time and other software like MATLAB, Python, or iSight?
Yes, in general, the interface between VI real-time and external optimization software is pretty open. As a built-in feature, ViaGrade is providing a set of API that are allowing to call VI real-time from a MATLAB environment. But in general, it is also possible to interact with the workspace that is generated by VI real-time from an external environment. So also Python or other tool can be easily accessing the data from VI real-time and being integrated into the optimization simulation loop.
Okay. So yeah, thanks everyone for your questions and also for the answers. So that brings us to the end of the Q&A session and also the end of this webinar. As I said at the start, the whole webinar is being recorded and will be made available on our webpage soon. And of course, if you have any questions or you're interested, please click through the links shown earlier in the presentation. Additionally, we've also put into the chat a link to a survey. So we would appreciate if you could take the time to fill out this survey. It's very useful for us. And yeah, so thank you everyone for joining us today and have a good day.